Good morning, all of you. Welcome to another session on data mining. In the earlier session, we have looked into what association rules are, how association rules play a major role in market basket analysis. And we have seen how to mine these association rules from given databases. In a database of all transactions happening at the store, an association rule is something that defines a frequent pattern according to the frequency in which it occurs and associated support and confidence values. That's what an association rule is. Now, to identify this association rule, we need to find a frequent pattern that frequently occurs, and we need to find two mathematical measures called as support and confidence, based on which we will define that frequent pattern as an association rule. So this association rule includes the support and confidence value, and this association rule helps us to predict the future. So something that has happened earlier is what I call as a frequent pattern. And with the mathematical measures associated with it, the support and the confidence value, I can say how much of it is possible in the future. So with this in mind, we have looked at two different algorithms that can help us mine association rules. The first one was called as Apriori algorithm, and the second one is called as the FP growth algorithm, or the frequent pattern growth algorithm. In Apriori algorithm, it is based on the a priori principle, which says if any set is not frequent, then none of its supersets will be frequent. So that is the basic principle in a priori algorithm. So what they do is they scan through the database multiple number of times. Each time they generate a set of patterns with n item sets. So in the first iteration, a priori generates item sets with one item in them. And in the second iteration, a priori generates item sets with two items present in them. So that becomes the two item set. And in the third iteration, a priori generates item sets with three items. So it's called as three item set. So every iteration of scanning on the database, a priori generates a set of item sets. And then once it identifies the all possible combination of item sets, that is called as candidate generation. Each of the possible item sets are called as combinations are called as candidate item sets. We are going to use these candidate item sets and then run another scan through the database to find out their support values. Or then we are going to count the number of transactions in which that particular combination occurs. That's how a priori works. And then we saw FP growth algorithm. The major disadvantage in a priori algorithm is that the algorithm, the computer is forced to scan through the database multiple number of times. So I have a requirement to scan through the database once for candidate generation, another for support value calculation, and support value calculation for every combination we run a scan through the entire database once. So it's a very voluminous task. In order to avoid this, we started designing the FP growth algorithm, or the frequent pattern growth algorithm. In the frequent pattern growth algorithm, instead of scanning through the database multiple number of times, we are going to generate a tree structure which is done by scanning through the database once. And once the tree structure is ready, I am going to refer only to the tree structure, either for identification of frequent pattern or for calculation of support. So I am not going to scan into the database again. So I am going to scan the database only once. That is called as the FP growth algorithm. Now we have seen these two algorithms earlier. we will look into one example and we will work out the same example with the a priori algorithm and the same with FP growth algorithm. Then we will understand the difference between the efficiency of these two algorithms. This is how you will be asked in your examination also. So with that in mind, I'm just telling you the question. You can take down the question here. Following a data is given a database of 5 transactions. Let minimum support be 60 percentage and minimum confidence be 80 percentage. So I am given a database and I am going to work out this using a priori algorithm. And the question that is given to me is, first value is minimum support threshold is given as 60 percentage and minimum confidence value is given as 80 percentage. Okay, so they say a database has 5 transactions. Let the minimum support value be 60 percentage and the minimum confidence value be 80 percentage. Now these are the transactions in the database. So I have a transaction ID followed by the list of items that were purchased in that particular ID. So the first one is T1. In T1, these are the items purchased. M, O, N, K, E, Y. So I have got 6 items purchased in the first transaction. The items are M, O, N, K, E, Y. Each of these may be IDs. They can represent mint, onion, like that. So I'm just, it's not just monkey that I'm trying to purchase. This is the question given in your textbook also. Now, the second transaction includes 6 different items: D, O, N, K, E, and Y. The third transaction has got 4 items: M, A, K, E. So it has got 4 transactions. The fourth transaction has got 5 elements. M, U, C, K, Y. And the fifth transaction has got 6 items: C, O, O, K, I, E. So these are the list of items that are purchased in a given set in some store. Now, in your question it is asked, find all the frequent item sets using a priori and FP growth algorithm respectively, and you try to compare the efficiency of the 2 mining processes. Once you complete your mining process, list all the strong association rules with the support and support C and confidence yes using in a form given using the meta rule here. So I'll write a meta rule, and in that format we are supposed to mention association rules with 3 item sets. So this is the meta rule format. We indicated with a dash in between means for all. So a V with a bar in between is called as for all. Now I'm not sure if you are able to see this. Okay. For all X, a C and a line in between indicates belongs to. So for all X belongs to items. So X, I am going to take it as one specific item given in the transaction. So for every transaction, we are going to find out which are the frequent pattern. So for every X belonging to some transaction, then I have to mention a predecessor and a consequent. So my predecessor is buys X comma item 1, some item 1, and is mentioned using a power symbol or an inverted cap symbol. Buys X comma item 1 and buys X comma item 2. I've got two predecessors. Then the consequent is buying of another item. So buys X comma item 3. So this becomes my consequent with a support value of S and a confidence value of C. So all the rules that we mine using a priori algorithm, we are going to put it into this form for the result. Now how does the a priori algorithm work? Now for the a priori algorithm, we know it works in two phases. So multiple iterations, it works on the same database, same set of transactions, and it generates a set of candidate item sets in one phase, and in the other phase, it prunes out some samples. So the idea is you perform join and prune step iteratively on a database. So this is the database we have here, a database of 5 transactions. We are going to run through this database multiple number of times and find out in every iteration we are going to perform one join step and one prune step. In the join step, we are going to generate frequent candidate item sets that are all possible combinations of some n number. Now, in the first iteration, I generate all possible values of one item set. In the second iteration, I generate all possible combinations of 2 item sets. In the third phase or the third iteration, I generate all possible candidates of 3 item sets. Likewise, so for every phase, I generate all possible combinations of n item sets. And in the prune phase of every iteration, I scan this database and find out the support value for that particular combination. So for every combination listed in the candidate item set, we are going to scan the database once and find out the support value. That's the prune phase. So if the particular combination does not have or satisfy the minimum support value, then it will not enter into the frequent item set. Now with this in mind, we are going to draw the first phase. The first iteration 1, I am going to perform the join step. In the join step, we are going to list all possible candidate 1 item set. So I am going to define it as C1. C1 means all possible combinations of one item set. So what are the item sets we have? I have so many items in my database here. M is one item, O is one item, N is one item. Like that I have multiple items here. So I'm going to list all of these items and I'm going to find out the list. Okay, now this is my list. M O N K E Y. Another one is D. And the rest of it I've already listed. M is already there. Another one is A. K is already there. E is already there. In transaction ID 4, M is already there. U. So I'm adding U. C. K is there. Y is there. C is there. O, K. I'm going to add I. E is already there. So these are the possible one item sets. So these are the possible one item sets, or this is called as C1 or candidate one item sets. Okay. Now when I've got all the candidate item sets, my next step is to scan through the database and find out their support value. So I have to find out the support value of each of these item sets. Yeah. Support count means the number of transactions in which that particular item is present, and support means out of the total number of transactions, in how many transactions that particular item is present. That is called as support. So there is a difference between support count and support value. Support count is the number of transactions. Support value means the probability or the actual number of transactions out of total number of transactions. Okay. So I am going to find the support value here, not the support count. In the support count, what is the support count of M? M is present in transaction ID 1, transaction ID 3, transaction ID 4. So I have got 3 different transactions in which M is present. So the support value of M is 3 out of total number of transactions is 5. So my support value of M is 3 by 5. Okay. What is 3 by 5? Is it above 60%? Okay. So 3 by 5 means 63 odd percentage. So it's above 60%. So I am satisfying the minimum support value for M. The same way I am going to do for O. O is present in how many transactions? It is present in transaction T1, T2, and in T5 it is present twice. So I have to count it as 2. So I have got 4 transactions, 4 times in which O is present. So 4 out of 5 transactions have O. So my support value is 4 by 5. And N is present in 1, 2. 2 transactions. So its value is 2 by 5. K is present in 1, 2, transaction 1, transaction 2, transaction 3, transaction 4 and transaction 5. So it is support value is 5 by 5. And E is present in transaction 1, transaction 2, transaction 3 and transaction 5. So E's support value is 4 by 5. Y. The next one item set is Y. Y is found in transaction 1, transaction 2 and transaction 3. So it is 3 out of 5. Then we go in for D. D is present only in one particular transaction. So its support value is 1 by 5. Then we have A. A is also present only in one transaction. So its support value is 1 by 5. And then you have U. U is also present only in one transaction. So it's 1 by 5. Then you have C. C is present in transaction 4 and 5. So we have got 2 transactions that carry the value C. C support value is 2 by 5. and we have I at last. I is present only in the last transaction, transaction 5. So its support value is 1 by 5. Right. Now I have calculated the support values of all possible one item set. Now with that in mind, I should now identify if let me. Now I should identify if my okay. I think this would be better for you people to see. So I've got transactions. All one item sets are listed here and all their support values are listed here. I'm clear, I guess. Now we move on into the second phase of this iteration, which is the prune step. What does the prune step say? If their support value is less than the minimum threshold, then I should not consider them as frequent. Now, my minimum support value, which is given in my question, is 60%. So it is not possible for me to consider any of the item with less than 60% support value as frequent. So in this, tell me which of them are having support value of greater than 60%. 3 by 5 is greater than 60%. So M will be there. 4 by 5 is there. 2 by 5 is not there. So 2 by 5 is less than 60%. So it cannot go into the frequent item set. And 5 by 5 accepted. 4 by 5 for E is accepted. Y 3 by 5 accepted. D 1 by 5 not accepted. A 1 by 5 not accepted. U 1 by 5 not accepted. C 2 by 5 not accepted. I 1 by 5 not accepted. So what are the frequent items here? The frequent item is called as L1. L1 means list of one item sets that are frequent in the given database. So which are the frequent items here? M, O, K, E, Y. M-O-K-E-Y. These are the only items which are having a support value given satisfying the minimum support threshold. So these are taken into the next level. So this is my first iteration. My first iteration is complete here. In my second iteration, I have to scan through this L1 and form all possible combinations of L1. So that process is called the join step. It is the candidate generation process. So I have to generate C2, which includes all possible combinations of L1. So in L1, when I form combinations, I should check M with O, M with K, M with E, M with Y. That is the way I draw out all the possible combinations. Then I should go with O with K. OM will already be there. MO and OM are the same thing. So I am not going to worry about that repetitive combination. So the second set will be OK, OE, OY. Likewise, I am going to generate possible combinations. Now, let me list in C2. Now, in C2, we will not require the a priori principle because using L1 we are generating C2. I'll tell you why we will not require a priori principle. When we generate C3, we will understand the impact of that a priori principle. Now list out only two combination of all possible combinations of two item sets. So I should have a set. In the set I have M, O, M, K, M, E, M, Y, then I will extend the C2s here. OK. OK means O and K are items here. I'm not saying OK here. OK, OE, OY. This is for O. Then KE, KY. KE, KY. And then we also have EY. I'm listing EY here itself because I'm not having sufficient space. I'm writing EY here. So these are my possible items. So I've got items, right? Now with these items, I should look for my joint step is over now. The next phase in the same iteration is prune step. In prune step, I have to look back into the database and find out the support value of these combinations. So when I say support value of this combination, I should check number of transactions in which both M and O are present. If both of them are present, I should count that in, and that count in proportion to the total number of transactions gives me the support value. Now let me take M and O combination. In how many transactions it is present? I've got transaction 1 in which M and O are present. In no other transaction, M and O are present together. So its support value is 1 by 5. Are you able to understand? Now MK combination. MK combination seems to be present many number of times. In transaction 1 we have M and K. In transaction 3 we have M and K. In transaction 4 we have M and K. So we have got 3 transactions in which M and K are present together. So it is 3 by 5. So out of 5 transactions, in 3 transactions we have both M and K occurring together. Now check M and E. M and E are present in transaction ID 1 and transaction ID 3. In monkey and make we have M and E combination together. So it is 2 on 5. Then check for M and Y. M and Y is present in first transaction. M and Y is present in fourth transaction. So it is 2 on 5. Then you go for EY combination. In EY, we have transaction ID 1 has got EY, transaction ID 2 has got EY, and nothing else. So we have got 2 transactions in which E and Y occur together. So it is 2 by 5. Now see the rest of C2. Okay. Check how many are having O and K together. Transaction 1, transaction 2 and transaction 5. So we have got 3 transactions out of 5 which has got both E and K together. Then OE. OE is present in 1, 2 and 5. So there are 3 transactions in which O and E are present. OY. OY is present in transaction ID 1 and transaction ID 2. So it is 2 on 5. KE. KE is present in a lot of transactions together. T1 has got, T2 has got, T3 also has, T5 also has. So it is 4 on 5. And KY. KY is present in 3 transactions. Transaction ID 1, transaction ID 2 and transaction ID 4. So I've got 3 on 5. Now when I look at this itself, I understand that so there are certain elements that are continuously purchased together. I can see K and E are continuously purchased together. Out of 5 transactions, I've got 4 transactions in which K and E are present together. So like this, I can understand manually, but I'm going to still formalize this and see how much sure I can be of this particular pattern. Now I can see that it is a frequently occurring pattern, almost, but with what level of confidence and support. That is my next understanding. So in iteration 2, I have completed the join step. Now I should move on into the prune step of iteration 2. In prune step, what do we do? In prune step, we calculate looking into the support value, whether if they satisfy the minimum support threshold, we will take it as frequent item. If not, we will have to eliminate that particular combination. So I am forming L2 here. Minimum support value means I should, because it's mentioned as 60% here, anything above, anything with the support value of 3 by 5 or above will be having more than 60%. So MO combination has got support value of 1 by 5. It is not accepted. MK has got 3 by 5, accepted. ME support is 2 by 5, not accepted. MY support is 2 by 5, not accepted. EY support value 2 by 5, not accepted. OK 3 by 5, accepted. OE 3 by 5, accepted. OY 2 by 5, not accepted. KE 4 by 5, accepted. KY 3 by 5, accepted. So this is performed in the prune step, and I have got certain combinations which have satisfied the minimum support value. I am going to put them into L2. What are the combinations I have? MK, O with K, O with E, K with E, and K with Y. So I have got 5 combinations in L2 which satisfy the minimum support value. Now I have got 5 combinations here. So my second iteration with 2 item set is complete. I proceed into the third iteration. In third iteration, I form combinations of 3 elements. So it is called as 3 item set. From L2, I have to generate C3. That is the join step of third iteration. Now, how do I generate C3? When I generate C3, I am going to make use of the a priori principle. I am telling you. So, in this, all possible combinations of L1 we have directly taken into C2, because if I consider M and O as one group, what are its subsets? M individually is a subset, O individually is a subset. What does the a priori principle state? It states, for any frequent set, all of its subsets have to be frequent. Okay. In the case of MO in C2, which is a 2 item set, individual 1 item sets of M and O, both of them are frequent. They are present in L1. So, if any time I form combination C2, all of their individual subsets will be available in L1. So, I need not use the a priori principle when I am generating C2. That is not the case when I am trying to generate C3. Let me give an example. Now, I have got some combinations here. Okay. MK is there, OK is there. What is the possible combination I can generate from this? M, K, O. Okay. M, K, O. Now, if this is a superset, what are its subsets? Its subsets are M individually, K individually, O individually. Are all of them frequent? M, K and O, all of them are in L1. So not a problem. Now what are the two item sets for the three item set combination? MK is 1, KO is 1, EMO is 1. Right? So I've got three possible two item sets here. For this three item set combination, I have got three possible two item sets. MK, KO and MO. Now I should check if all of them are present in L2. Is MK present? Yes, present. Is KO present? OK is present. So done. Is MO present? No, it is not. So the combination MKO cannot be frequent because one of its subsets, which is MO, is not frequent and it is not available in L2. So when I try to generate C2, I have to combine 2 of each and find out if all their subsets of that particular superset is available back in L2. So we will try this out. So I'll write the combinations first. Then we will check back with L2. The combinations are MKO from these two. Then I'll take the next two. OKE is one combination. If I take these two also, I get OKE only. Then I got KEY as one combination. So when I generate, I have to generate this way again. So MK with OK I tried up. MK and OE. I can't form a three item set. MK with KE. So I can form as MKE. MK and KY I can form MKY. Now OK I should try with these others. OKE I have listed. OK with KE, that's the same. OK with KY. OKY is one combination. Now OE with all the others. If I form OE and KE, OKE it is already there. OE and KY, I can't form a three combination, so I can take it. Then I should look into these two. KE and KY, I've listed it already. So these are the possible combinations from L2. Now I should check if all of them can be considered as a candidate using the a priori principle. In this, what are the subsets? I have to check MK, KY and MO. I found MO is not present, so this cannot enter into C3. Then this combination OKE, OK, KE, OE. All of them are present in L2. OK is present, OE is present, KE is also present. So I can consider this. This can be in C3. Then the next one is KEY. What are its subsets? KE, EY and KY. KE is present in L2, EY is not present in L2 and KY is present. So this cannot come into C3. The next is MKE. In MKE, the subsets are MK, KE and ME. MK is present, ME is not present, so this is not possible. Then we have MKY. MKY subsets are MK, KY and MY. MK is present, KY is present, MY is not present, so this cannot come into C3. And then OKY. In OKY, we have subsets as OK, KY and OY. OK is present, KY is present, OY is not present. Done? So this also cannot come into C3. So I've got C3 though. There's only one possible combination which can come. Which is OKE. Now I should find the support value of OKE. OKE combination, let me check with my database here. When I look into my database, OKE is present in 1, 2 and transaction 5. So its support value is 3 by 5, which is around 66%. So it satisfies my minimum support value. So I am going to calculate the confidence value of this transaction. When I look into the confidence value means out of the transactions in which the predecessor is present, how many transactions have the consequent also. Now, which is my predecessor? O and K are my predecessors. E is my consequent. So I have to check the number of transactions in which O and K are present together. So let me check O and K combination. How many transactions have O and K? You've got 3 transactions in which O and K are present together. So out of that 3 transactions, all the transactions have E also together. So the confidence value of OKE is total number of transactions in which O and K are present, and out of that how many have E together. So that is also 3. So 3 upon 3. 100% confidently we can say that if O and K are purchased, E also will be purchased. Do you understand? So it satisfies my minimum confidence requirement also. My minimum confidence requirement given in the problem is 80%. I have got 100%, which is 3 on 3, which is 100%. So I have to now write the meta rule for this. In the meta rule, I've got a format for writing my meta rule. So I am writing it in that format. For all x belonging to transaction. What is my transaction? So I have to write it as TID. Okay. It has got TID there in my table. TID buys item X. X comma item 1. Item, what is item 1? My item 1 is O. X comma O. And buys X comma, in that transaction I should also have item K, X comma K. Then it implies that they also buy, so buys X comma, what is my consequent? Product E. And what is my support value? Support value is 3 by 5, which is 66%, and confidence is 100%. So this is my association rule which I have generated from the given set of transactions. I hope all of you have understood this. We will solve the same example using frequent pattern growth algorithm in the next session. With this, I'll stop for today's session. Thank you one and all. Stay home, stay safe. Looking forward to seeing you all in person very soon. Thank you all.